Question number 1. Use the given graph of f of x to find the intervals on which the function is increasing. Recall that, with increasing, as you move left to right, the y values are getting larger. So as you move left to right, your graph is rising. Okay. So looking at my graph here, if you notice that, on this part, moving, left right here, I'm falling, I'm going down, so that's decreasing. Then right around here, it kind of turns, and this part here, I'm going uphill, so I'm increasing. And then again, this last part, I'm falling, so I'm decreasing. So it looks like I'm increasing on the interval, like I said, from here to here. Now remember that we're supposed to be giving the x values. So if you look on our x-axis, that's going to be from about here to here. So, this piece of the x-axis, so it looks like from -3 to +3. Okay. And then I'm going to go ahead and the question it asks for this, I'm also going to list where it is decreasing. So anywhere, like I said, if it is moving from left to right, the y values are getting smaller, so it's kind of falling. That's where it's going to be decreasing. So go ahead and try this right now on your own. You can see from here to here, it's falling, it's decreasing, and then, like I said, we're increasing, and then from here to here, it's decreasing. So on our real number line, it's going to include these areas. So we're going from a -infinity to -3, and then union the interval from 3 to +infinity. And let me go ahead and point out one more feature of this graph. If you, right here where it changes from decreasing to increasing at this point, that's going to be a relative minimum. So I'm going to have a relative minimum or a local minimum at x equals -3. And then right here where it's increasing and then decreasing, so at this point we have a local or a relative maximum. So I have a relative max at x equals +3. Question number 2, find the intervals where the function has the indicated concavity. So we're looking for where the graph is concave downward. I'm also going to list the intervals where it's concave upward. Okay, so for concave downward, remember this is concave down, and concave down can also look like this. So this first one here, this is concave down and increasing. This is concave down and decreasing. So looking at my graph here, this part I'm going up. And then if you look between -1 and +1, so here I'm concave down right here, but then I'm concave upward again. And then if you look from 1 to infinity, this is all concave down. So I'm going to be concave down on the interval from -1 to 0, and then again from 1 to infinity. And like I said, let's go ahead and do concave upward. So from -infinity to -1, I'm concave up here. And then on this piece of the graph, I'm also concave up. So concave up, increasing, concave up, decreasing. So concave up on the intervals from -infinity to -1, and then again from 0 to +1. With concavity, we also have, or sometimes we'll find an inflection point. So an inflection point is where the concavity changes, but in order to be an inflection point, it also has to be in the domain of our graph. So if you notice here, my concavity changes. At -1, it was concave up and then concave down, but -1, x equals -1 is not in my domain. That cannot be an inflection point. So I do have an inflection point though here at 0. So an inflection point at x equals 0, because it's a point, it's in my domain, and then concavity change from down to up. So that makes it an inflection point. Question number 3, find y double prime for the function. So we're asked to find the second derivative. The rules are the same for the first derivative and second derivative, but I do need to find and simplify my first derivative. I'm going to get to the second one. Okay, so notice here that I've got this fraction. There's 2 possible solutions for this one. I could use my quotient rule, or, and this one will be a little bit easier rather than the quotient rule, is I can bring my denominator up and write this as 3x plus 4 to the -1 power. And then I can go ahead and I can use my general power rule. So that's how I'm going to approach this one here. It'll be less work than the quotient rule. But if you use the quotient rule and you simplify everything correctly, you'll get the same answers. Okay, so this is what y is equal to. So my first derivative, so I have to bring down my exponent. So I've got a negative here already. So I bring down my -1, decrease my exponent by 1. So now it's to the -2 power times the derivative of what's inside here. So times 3. So my first derivative, I'm just going to simplify this a little bit, bringing my coefficients together. So that becomes a positive, and I have the 3. So I've got 3 times 3x plus 4 to the -2. Now I'm going to go ahead and take the second derivative, again using my general power rule. So I have my 3 here already, so I bring down my exponent. So I bring down, I multiply the -2. I'm going to decrease my exponent by 1, so 3x plus 4 to the -3rd power, and then times the derivative of what's inside, so times 3. And now I have y double prime equals, so I've got the 3, -2, and this 3, so I get -18 times 3x plus 4 to the -3 power. I'm okay with you leaving your answer like this, but since we have to match the multiple choice answer, we're going to have to rewrite this without the negative exponent. So I have a -18 all over, and this will come down 3x plus 4, and now it's to the +3 power. And there's my final answer. Number 4, use the first derivative test to determine the local extrema, if any, for the function. The first derivative test, pretty much what we're going to do is look at the plus and minus chart on our first derivative. And then we'll see where it goes from increasing, decreasing, decreasing, increasing, and stuff like that. Okay, so first I got to find my first derivative. So we have f prime of x. It's going to be 12x to the 3rd minus 12x. Now I need to know where this is equal to 0 or undefined. Those will give me my partition numbers. It's a nice polynomial. It's not going to be undefined anywhere. And I cancel this by factoring. So I'm going to take out the 12x. And this leaves me with x squared minus 1. And then I will factor even further. So x minus 1, x plus 1. So this means that my partition numbers are going to be x equals 0, 1, and -1. These are also my critical numbers because these partition numbers from the first derivative are in the domain. Okay, so let me go ahead and set up our plus and minus chart over here. And again, I got my -1, 0, and 1 go on here. Now, some students, there could be some variation in how you do your plus and minus chart. I do have students who will take their test point and plug it in and just get the number. I will look at just the sign when it's factored like this. So you may do it the other way. It makes no difference to me as long as you show me some work. All right, so I need a test point somewhere between -infinity and, -1. I'm going to go with -2 as my test point. So when I plug it in, remember, I'm going to be plugging it in right here where my first derivative is. So I need to plug it in for all my instances of x. So I have 12 times a -2 is going to be a negative. And then -2 minus 1 gives me a -3. And then -2 plus 1 is a -1. So a negative times a negative times a negative gives me a negative, which means my graph is going to be decreasing on that interval. Now I'm going to pick a test point between -1 and 0. I'm going to go with a -0.5 or -0.5 if you prefer the decimal. So again, plug it in here. So 12 times a -0.5, that's going to be a negative. And then -1/2 minus 1 is a negative, and then -1/2 plus 1 is a positive. So negative and negative positive is going to be a positive result, so we will be increasing. Same thing between 0 and 1. This time I'm going to use a positive 1/2, plugging it in all my places. So 12 times 1/2 is positive, 1/2 minus 1 is a negative, and then 1/2 plus 1 is a positive. So positive, negative, positive, or positive, and we will be, oops, I'm sorry, not positive. We're negative there. Sorry, we are negative there, and therefore it is decreasing. And I need one more test point. I am between 1 and infinity. I'm going to go with 2. I could use 5. So 12 times 2 is positive, and 2 minus 1 is positive, and 2 plus 1 is positive. So positive, positive, positive is positive, so we are increasing. Okay, so for my plus and minus chart, I can tell where the function is increasing, where it's decreasing, but I can also find my relative or the local max and min. So whenever you are decreasing and then increasing, you're going to have a relative minimum. So I have a relative minimum at x equals a -1. And then here, notice at 0, I am increasing and then decreasing. So that's going to give me a relative maximum. So relative maximum at x equals 0. And then also notice right here at +1, it is decreasing and then increasing. So that's also going to be a relative minimum. So I have a relative minimum at both x equals -1 and at x equals a +1. So 2 relative minimums, 1 relative maximum. Okay. And then again, just remember that the first derivative test says if you are increasing and then decreasing, that's going to give you a relative max. If you are decreasing and then increasing, this is going to be a relative min. If you are increasing and increasing, or decreasing and then decreasing, it'll be neither a max nor a min. And then the other thing you have to keep in mind is in order to be a relative max or relative min, that x value has to be in the domain of your original function. Not a problem for this one because it's a polynomial, domain's all real numbers, but it is something you want to be aware of on future examples. Number 5, determine the intervals where f of x is decreasing. Okay, so again, increasing, decreasing, relative max and min, you're thinking first derivative plus a minus chart. Okay, so taking the derivative of this function, I do have a rational function I'm looking at using the quotient rule. So f prime of x is equal to, so the quotient rule is derivative of the first times the second minus the derivative of the second times the first all over the denominator squared. And I'm going to have to simplify this because I need to find my partition numbers. So distributing here, I get 2x squared minus 6x minus x squared all over my x minus 3 squared. Combining like terms in the numerator, 2x squared minus x squared, so I have x squared minus 6x all over x minus 3 squared. I'm going to factor a little bit more, so I'll take out the x from the numerator. So then x minus 6, and this is all over x minus 3 squared. Okay, now that it's completely factored, I can easily find my partition numbers. So my partition numbers, again, this is wherever it is equal to 0 or undefined. So anywhere the numerator or denominator equals 0. So x could be 0 or 6, and in the denominator, we get x equals 3. Okay, so these are going to be my partition numbers. They may not all be critical numbers, because again, it had to be in the domain of the original. So if we look real quick, the original function, x can't be a 3, so critical numbers are 0 and 6, but all 3 of these are partition numbers. Okay, so here's my real number line, and I'm going to have 0, 3, and 6 on here. So going with my test points, something between -infinity and 0, I'm going to go with -1. And again, I am plugging it in over here for all my x's. So -1 in the numerator, and then -1 minus 6 is a negative. And then when I plug it in the denominator and I square it, it's positive. So I get negative, negative, positive, which will be positive. And therefore, I'm increasing on this interval. Between 0 and 3, I'm going to go with a +1. So plugging in for x, I get a +1. 1 minus 6 is a negative. And in the denominator, I plug it in there, then I square it, positive. So positive, negative, positive gives me a negative. And I am decreasing on this region. Between 3 and 6, I'll use test point of 4. So plugging in for x, I get a positive. 4 minus 6 is a -2, so negative. And the denominator, positive squared, is positive. So again, positive, negative is a negative, and I will be decreasing. And now choose a number that's larger than 6, somewhere between 6 and infinity. I'm going to go with 7. Plugging in 7 for x, I get a positive. 7 minus 6, positive. And then the denominator, that's always positive. So positive, positive, positive. It's going to be increasing. Okay, so this particular question asked me to list the intervals where it was decreasing. So it's going to be decreasing on the intervals from 0 to 3, and then again from 3 to 6. And then if I had asked you on which intervals is it increasing, It's increasing from negative infinity to 0, and then again from 6 to infinity. And then on the test, usually I'll ask you, both. Tell me where it's increasing, tell me where it's decreasing, all of that in one question. Okay. We could talk about relative max and min just because I have all the work here done. Notice that I do have a relative maximum at x equals 0 because it's increasing and then decreasing. And then I also have a relative minimum at x equals 6 that's decreasing and then increasing. Okay. But for this one, I was just asked, where's it decreasing? Determine the intervals over which f of x is concave upward. So to find where a function is concave up, concave down, or inflection points, you need to do a plus and minus chart on the second derivative. So I'm finding my first derivative, f of x, I'm using my general power rule. So I bring down my exponent, I decrease it by 1, so my new exponent is 2, and then times the derivative of what's inside. So my first derivative is equal to 3 times x plus 3 squared. And now I'll take the second derivative. Again, I'm using the general power rule. So I have my 3 here already. I bring down my exponent, so multiply by 2, and x plus 3, decrease my exponent by 1, and then multiply the derivative of what's inside. So my second derivative, multiplying all these my coefficients together, I get a 6 times x plus 3. Okay, so what are my partition numbers going to be? So again, anywhere this is equal to 0, 6 can't equal 0, but x plus 3 will give me x equals a negative 3. That's my partition number. All right, that's great. I only have one partition number, which means 2 test points. Okay. Picking a number to the left of negative 3, so something between negative infinity and negative 3, I'm going to go with negative 4. And again, I am plugging it in, right here. So negative 4 plus 3 is a negative 1 times a 6 is going to be a negative. That means it is concave downward. Between negative 3 and positive infinity, 0 is the easiest choice. I always go with 0 when I can. Plugging in a 0 for x. So 0 plus 3 is positive times, 6, that's positive, so will be concave upward. And again, this one here asking where is it concave up, so I'm going to say it's concave up on the interval from negative 3 to infinity. And like I said, on the test, I'm also going to ask you, where is it concave down? And so this one is going to be negative infinity to to negative 3. And then let's just throw in that extra here. Do I have an inflection point? So again, to be an inflection point, the concavity has to change, and it has to be in the domain. So I do have an inflection point at x equals negative 3. Find the inflection points for f of x. Okay, so like the previous example we talked about, inflection points, I need to do a plus and minus chart on my second derivative. So I have f prime of x is equal to 3x squared minus 6. And now taking the derivative of this function, we get 6x plus a 0. Okay, so f of x equals 6x. That means I have one partition number, and that's going to be at x equals 0. So setting up my real number line, 0. Test point between negative infinity and 0, I'm going to just go with negative 1. And when I plug it in here, my second derivative, 6 times a negative 1 is negative. So it's going to be concave down. Plugging in, I'm going to go with positive 1 for the other side. 6 times positive 1 is positive, so it's going to be concave up. And so my inflection point is going to be at x equals 0. And again, make note that the concavity has to change at that point, and it has to be in the domain of your function.